Okay, hello everybody. My name is Silvina Hanono Wachman. I'm the co-lecturer for 6004. So starting today, you'll see me up here for a few weeks. So first thing I want to mention is you'll notice that there's a second handout. We'll get into that. You don't really need it for today's lecture, but you will after today. The other thing is that basically we're going to start a really exciting part of the class today, which is building a general purpose computer. So far we've learned about a lot of interesting things. We've learned how to use transistors in order to build logic gates. We've learned how to put these logic gates together in order to make more complicated functions. And then we went on to even sequential circuits where we were able to save state. So today we're going to go a step further than that. So let's start off with a simple example. We have a function that we want to be able to solve. This function is factorial. You should all probably be familiar with it, but basically it's n times n minus 1 times n minus 2 and so on down to 1. And here we have a very simple piece of code in C which implements this. You have two variables, a and b, and a is keeping how much you've multiplied so far, and b is the next number to multiply. So essentially every time through the loop you multiply a times b and then you decrement b, and you keep doing this until as long as b is not equal to 0. Here what we see is a high level FSM, which basically says I have three main states here. I have a start state, which is my initial state. I then have a loop where I keep multiplying and subtracting until I finally get to my finished state, which is that b is equal to 0, and then I move on to done. So very quickly, let's just take a look at what the data path and control FSM for something that would be able to do factorial might look like. And so here we've put up the data path. What we've got is we've got two registers, A and B. We have two units that can do our multiplication and our addition, and then we have our multiplexers, which select the input that's going to be fed next into each of the registers A and B. We then add a little bit more logic over here, and this allows us to check, is the new value of b equal to 0 or not? It produces this new signal, which we call z for 0. And z is equal to 1 if b is equal to 0, and 0 otherwise. And now we can create our control FSM similar to how we've done so far in 6004. So z is going to be your input together with 2 bits of current state, since we have a total of three states. And then the output is going to be the next state as well as the WA select and WB select signals, which are going to tell the data path what it should do in order to actually perform this computation. So we're not going to actually follow this whole truth table, but you can look at it and convince yourself that this truth table will essentially go through the states of this FSM and compute factorial. Okay, so that's great. We know so far with everything we've done how to build hardware that's for a specific function, right? So today we're going to take that further, figure out how do we build hardware for any kind of program. So we're going to learn about von Neumann architectures, and another name for it is a stored program computer. And basically, this was introduced by John von Neumann in 1945. It consists of 3 components. The first is a central processing unit, which has 2 pieces to it: the data path and the control FSM, just like we saw in the factorial problem just now, except that this one's going to be a little bit more general purpose. So what does that mean? It's not only going to be able to do add and multiply, it'll be able to do more functions. It won't only have, the 2 registers A and B, it'll have a number of general purpose registers, and so on. The CPU needs to be able to talk to main memory, which is where we're going to store most of our data. And you can kind of think of main memory as a huge array of, let's say, W words, each of which is n bits wide. And nowadays, memories have gotten so cheap that even a small memory is going to have on the order of billions of words. And n is going to be at least 32 bits wide, often larger than that. And On the other end, what we have here is an input-output device. And so if you need to communicate with something like a keyboard or an external piece of memory that is even going to work when you turn your power off, this is how we would do it. Okay, so the main idea with a stored program computer is that we have instructions, which are basically just binary bits, which are telling the computer what to do. And so in our main memory, we're going to have two different types of information. We're going to have instructions and we're going to have data. Let's take a little bit of a closer look at that. So what's in an instruction? An instruction is going to have a bunch of fields, which is going to tell the computer what it needs to do. So the first thing it's going to have is an opcode. An opcode is something like add, multiply, shift, whatever it is that you need to do. It's going to be told where to get its source operands from. So this is RA and RB are basically just pointers to registers. And finally, it'll be told where the destination should go to, and that's going to be another register, RC. And so the way that this is interpreted is you're going to take the operation, perform it on registers RA and RB, store the result into RC. Okay, so what about data? Well, data can just be, some random number that it makes sense for my program and I need to have a place to store it. And so we're going to use memory to store that as well. So you might ask yourself, well, what's the difference, right? They're all just bits. How can I actually tell the difference of what's an instruction and what's data? And basically the way that that works is it all depends on how your CPU is using it. So if your CPU is taking something from memory and giving it to the control logic, that means it's an instruction. If your CPU is taking something and giving it to the data path, that means it's data. All right, so now we're going to take a little bit of a closer look at what the architecture of these kinds of computers looks like. So we said we have our data path. Here it is in more detail. And you see that this actually looks kind of similar to what we saw for the factorial program, right? We have a number of registers over here. We have an ALU, which can do a bunch of different ALU operations. ALU stands for arithmetic logic unit. And then we have some control signals, which specify where our operands come from and where we should write the result to. Our data path, as we said, needs to be able to talk to main memory. So what does it mean to talk to main memory? We said that main memory is basically this huge array. So in order to specify which piece of the array you want, you have to give it an index, or what we call an address. And so the data path is going to feed an address to main memory. And depending on whether you want to do a load or a store operation, you're either going to be getting data. So a load would bring data from main memory to the data path, and a store goes the other way around. Okay, then we have these status bits, which we see coming out here from the ALU. And so that would be things like the Z variable that we created. So this allows us to give data-dependent information to our control unit. So for example, if I want to do something only if a variable is equal to 0, that's how I would do that. Now the control unit also talks to main memory. Again, it's going to provide it with an address, and in this case the data goes in just in one direction where the instructions are fed to the control unit. The way that the control unit tells the main memory which piece of data to get is using the special register called the PC, which stands for program counter. So the program counter is basically just an address into the main memory, and it tells you this is the instruction that I want to fetch next. And then in addition to that, you'll have some control logic, some additional logic in the control unit, which decodes these instructions, and as a result of that decoding, can produce these control signals, which are sent back to the data path as A select, B select, the destination, anything else that you need to tell the data path so that it can actually do its work. So another way to think about it is that your data path is kind of the muscle of the system. It's doing all the hard work, all the computation. And the control unit is your brain. It's the one that's telling it how to go about doing those computations by setting the correct control signals. Okay, so instructions are basically our fundamental unit of work. And as we said before, it's just a bunch of binary bits. But those binary bits need to encode some useful information. So the information that they're going to encode is, first of all, an opcode, then source operands, and finally, a destination location of where we want to put our result. And in von Neumann architectures, the way that instructions are handled is basically implementing this loop here over and over and over again. So what happens? We first fetch our instruction. We then need to decode this piece of binary so that we understand what each one of those fields means. From there, we're able to read our source operands, execute the operation, write to our destination register, and finally compute the next PC. And so what's the next PC? Given that our instructions are just in sequential order in our memory, the next PC is calculated by simply adding the size of an instruction to the value of the current PC. And that will get us to the next instruction ready for the next cycle. Okay, so what's an instruction set architecture? Instruction set architecture is basically what tells us what it is that our machine can do. So it's going to define the operations that we can do. It's going to define what kind of storage capabilities we have. And it's basically, you can kind of think of it as a contract between the software and the hardware. What's nice about instruction set architectures is that it's a layer of abstraction. So if you recall from yesterday, I think last time's lecture, we were talking about multiple implementations of an adder unit. Right? So depending on what your constraints are, you might choose to make an adder that's faster, you might choose to make an adder that requires less area, etc. And so with our instruction set architecture, that information is not going to be provided for you. All you're going to be told is that your machine can perform an add operation, and how exactly it does that is hidden from you. The other thing that's nice about this layer of abstraction is that it allows us to separate our software from our hardware. And so the idea is that if we write a program today, I want that same program to be able to run on a machine with the same instruction set architecture 20 years from now. And so we can make lots of hardware developments in order to make our hardware faster, but that relationship between the software and hardware should remain the same. So here we show an example of an x86 architecture, which back in 1978 could run 330,000 instructions per second, and 25 years later, it can run as many as 5 billion instructions per second. But that same program will run on both of them. So the one kind of negative thing about the fact that many instruction set architectures last for so many years is that if you made a mistake, in defining what it should look like or how wide a particular field should be, then you kind of have to live with that mistake because you want your programs to continue to run. So let's try to understand that a little bit more, right? So it's actually pretty hard to design instruction set architectures. There's many, many, many decisions you need to make. So for example, we need to decide, well, how many operations should I support? Which ones should I support? And for every one of these decisions, they're basically trade-offs that you're making, right? So if I have, let's say I want to be able to do a fast Fourier transform. I may want to have some really, complicated instruction that would otherwise take me, tens of instructions to do. Well, there's a trade-off between that. On one hand, it makes the program a little easier for that particular application. On the other hand, supporting, such a complicated instruction is going to affect how I implement my hardware. Other types of things you need to consider are what types of storage do you have? How many of these general purpose registers make sense for me to have? Similarly, how do I go about, encoding the information in the instructions? So for example, if let's say that I decide that I should have 32 of these general purpose registers, then for each one of those fields, RA, RB, and RC, I'm going to need 5 bits, right? because 2 to the 5th is 32, in order to specify which of those 32 registers I want to use. But suppose 20 years from now, it turns out that I really wanted 64 registers and not 32. Well, I'm kind of stuck because my current instructions are not going to work if I now want to support 64 instructions. Okay, so how do we go about deciding which ones we're going to include? So, like engineers in general, the way we want to do this is in a quantitative manner. So we're going to use a bunch of benchmarks. We're going to have benchmarks that are good at different things. So some benchmarks might do a lot of computations. Another benchmark might do a lot of fetches from memory. Another, and so on and so forth. And there are actually suites of benchmarks that exist for us to use for this exact purpose. And so what we do is we take those benchmarks, we translate them into instructions that are using the instructions that are supported by this instruction set architecture that we're considering. And then we evaluate the performance. And even then, when we evaluate performance, right, we also need to know, well, what do we even mean by performance? Do we mean what's going to run the fastest? Do we mean what's going to require the smallest amount of area? We'll have to take that into consideration in making a decision about which parts of our instruction set architecture to include and which not to. But the main idea here is that the benchmarks are going to help you optimize the most common case, right? So if adds happen a lot, odds are that we want to implement it in a way that's small and fast and so on. So now we're going to actually start with designing our own instruction set. We're going to call this the beta. You're actually going to get to build this in lab. And so that's what the second handout that you have for today is. It's basically a description of the instruction set architecture for the beta. It tells you what the opcodes are. It tells you what the data path actually looks like. And over the next few lectures, you're going to become very familiar with all of this. All right, so the first thing is, what storage do we have available in our beta? So as we said, in order to be able to specify which address we want to fetch for our instruction, we have a special register called the PC, or program counter. We also chose to have 32 general purpose registers, which we label R0 through R31. And you'll notice that we actually use this notation R followed by a number just to remind ourselves that we're talking about a register. And we have one special register, which is this register 31, whose value is always going to be 0 because it's convenient to have that constant available to us at all times. And so what that means is that if I read register 31, I'm always going to get the value 0. If I write to register 31, it's effectively like I'm throwing out that data because register 31 is going to remain a 0. Okay, then the other piece of storage is our main memory. So if we have 32 bits that the PC can address, that means that we can address 2 to the 32 different locations. And the way that addressing works is that we address things in bytes. Bytes are 8 bits, but every piece of data in our beta is actually going to be 32 bits wide, or 4 bytes. So what you're going to find is that if you actually look at the addresses that are meaningful to us, they're always going to be in multiples of 4. So if one instruction is at address 0, which we label here in hex, the 0x, remember, is just telling you that it's a number in hex rather than binary, then the next one is going to be 0x04, then 0x08, and so on. And that's because each one of our beta words or instructions or even just data is going to be 32 bits wide, which is 4 bytes. Okay, so first question we want to ask ourselves in evaluating this is, why are we even making this trade-off between registers and main memory? And the reason there is because the registers are way, way faster than the main memory. So we could choose to create an architecture where every single operation has to communicate with main memory. So an add would get 2 operands from memory and then store its result into main memory. But the problem is that that would slow down our computer very much. And so we evaluate these trade-offs to decide, exactly which form of the operations we want to support. Okay, a little bit more on storage conventions. So because we only have 32 of these special purpose registers, we can't really use them to store things for a very long period of time. So any variable that we're really going to need, for an entire program, we really have to keep those in memory. And then we use the registers in order to calculate things temporarily. So for example, suppose that I want to execute this statement right here, y equals x times 37. We see that x is at address 0x1008, and y is at 0x100c. So what I actually need to do in order to perform this multiplication is I first need to get value x from location 0x1008. I bring that into my register, let's say register R0. I then multiply R0 by 37, store that result back into a register. In this case, we happen to pick R0 again. And then we take R0 and we put that back into the new location, the destination one, which is address 100C. Okay, now let's get a little bit more into our actual instructions, what we support and what this architecture can actually do. So there are three types of instructions. The first type are arithmetic and logical instructions. So these are things like add, subtract, multiply. There are Boolean operations like and or. It includes things like shifting operations or compare operations. Anything like that would fall under this category. We then have loads and stores, and that's what's going to be used every time we want to access something from main memory. Okay, so the general idea is we call these types of architectures load store architecture, which what that's going to mean is that anytime we do an arithmetic logic unit operation, that's just going to operate on the registers. But if we want to actually make use of something from memory, then what it's going to need to do is first load something, then do the operation, and then eventually store it once you're done. And finally, we have these branches, which allow us to change the PC by more than just going to the next instruction, right? And so sometimes we'll have a reason to not execute instructions completely in order, and so that's going to allow us to do that. So the next thing that I want to point out here is that we've decided for our beta architecture that all of our instructions are going to be 32 bits wide. So what do we think? Is that a good decision? Yes, why? Simpler. Right, so again, in general, this is a trade-off, right? If you recall from like lecture 1, we learned that if you have, if you use variable length encoding, you're probably going to end up with a smaller encoding, which means I could probably write a smaller program if I make my instructions be of different lengths. But that means that my decoding logic is also going to be much more complicated, and so once again, this is the trade-off that we've decided on, and that we've decided to go for simplicity, so all instructions are going to be 32 bits wide. All right, so now we're going to start to take a look at what the format of the instructions of the beta are. The first type of instruction is the ALU instruction, and it starts with a 6-bit opcode. It's followed by a 5-bit RC register, which is our destination register. That's followed by 5 bits of one of the source operands, which is RA, then another 5 bits of RB, and then the remaining of our 32 bits is actually unused. So to go a little bit more into detail remember that these are really just binary bits, and so we need to know how to interpret what those bits mean. And so we're going to have decoding logic that's going to know, oh, look, if I see 100000, that means that I need to do an add. Then if I see, the 5 bits, which represents the number 3 here, that means that I'm going to write to register R3. And similarly, my source operands are going to be R1 and R2. Now, if I was to take this 32 bits of binary and convert them into hex, I get this long thing 806110000, which obviously is not very intuitive if I'm trying to program my beta. And so instead of using the hex or binary, what we actually prefer to use are symbolic representations, right? It's much easier for me to look at this and say, oh, what I'm trying to do is add R1, R2 and put that result in R3, rather than figuring it out from this strange number. So what we're actually going to do is we're going to program in what's called assembly language, which are instructions that look like this. And then there's going to be a separate program called an assembler, which will convert those instructions to the binary that the control logic is going to make use of. Okay, so basically all this is saying here is that this instruction here is going to be interpreted as take the contents of register RA, add them to the contents of register RB, and store that into register RC. And so here we have the full list of all of the arithmetic ALU operations that operate on 2 registers that our beta is going to support. And so you'll become very familiar with all of these, but I'll just point a couple of them out. So this one, for example, stands for compare equal. This is compare less than or equal. And then these ones at the bottom here are shift operations. So this is a shift left, shift right, and this one is an arithmetic shift right. And we'll get into why those are useful to have. So our first implementation sketch, in order to support these ALU machines, looks like it basically did before, except that now things are a little bit more concrete, right? So now we've defined that we have 32 of these registers over here. We've also defined which operations the ALU can perform. And we've now specified that our sources are RA, RB, and RC. And so those are going to be our select signals for the multiplexers to tell the data path what to do. The other piece of hardware that we need is this PC logic, which is just going to add 4 bytes to the PC after every single instruction in order to get the address of the following instruction. Okay. So far so good. We can do quite a bit. And now someone poses a question to you and they say, well, is it worth it for me to, in addition to having all of these operations, also have an operation that can use 1 register and then a constant as the 2 source operands? And so, you look at them and you think, well, okay, how am I going to answer that question? And so, of course, we want to do it quantitatively, right? So we know that more opcodes is going to mean more complicated decoding logic, but more opcodes might mean that I can simplify my programs, I can use fewer registers, so it's got other kinds of advantages. So I'm going to take these same benchmarks that we used initially, and now you're going to translate them into this new form of your instruction set architecture, one that includes regular ALU operations and ALU operations that use 1 source register and a constant. And then you're going to evaluate them for performance and compare, how does it do versus the one that doesn't have these operations with constants. And you're going to determine whether or not it's worth keeping these types of opcodes as well. And what we find is that actually operations that use constants are extremely common. And so if we look at our benchmarks, we find that more than 50% of the executed arithmetic instructions actually use a constant. More than 80% of the compare instructions use a constant form, and about more than 25% of the load instructions use a constant form. And so basically what these results tell us is that it's probably a good idea for us to also support these kinds of instructions. And so we go ahead in our beta and also support ALU instructions with a constant. And so the format is very similar to what it was before. We have our 6 bits of opcode, 5 bits of the destination register RC, another 5 bits of RA, and then the remaining 16 bits are used as the constant. Now, a couple things to note here. The first thing is that the opcode RC and RA fields are using the exact same bits of our instruction that they use for the other type of operations. So what does that mean? What is the benefit of that? Is there something that I can reuse because I do that? The main idea is that it allows us to reuse some of our hardware, okay? And so some of the logic that controls how the data flows through the data path is going to be able to be reused for different types of operations by making this kind of design decision. Okay, so let's take a little bit of a closer look at what an operation in an instruction with a constant might look like. And so you'd have a different opcode here. And so this one, which is 110000, is telling the beta that it wants to perform an add C, which is an add with one register and one constant as its sources. And the other thing it's telling you is that the destination is going to go into R3. The first register that you're going to use is RA, and then it gives you this 16-bit constant in 2's complement representation. So hopefully by now we're all experts with 2's complement, and we can figure out that this number is actually -3. And so what this operation is doing is it's adding R1 plus -3 and then storing that result into register R3. Now there's one problem here, which is that my data path is actually a 32-bit data path, not 16 bits, and this constant is just 16 bits. So I actually have to do something to this constant in order to make it work properly. And what it is that I have to do is called sign extension. Any ideas what sign extension might mean? Take a guess. Yeah. Right, and how would you do that?
By like copying over the 1 and 0 at the very left.
That's exactly right. So if I have a positive number with 16 bits, then the most significant bit is a 0. If I then take that 0 and I make 16 more copies of it in front of my number, I'm still going to have the same value of my positive number. It's just now going to be a 32-bit representation of that positive number. And what's great about 2's complement is that turning a negative number from 16 bits to 32 is actually very easy. All you're going to do is you're going to take that most significant one and replicate it in the top 16 bits, and that is going to end up with the same number, which has a value of -3. Okay? And so it requires really hardly any hardware at all in order to be able to support the sign extension in our beta. Okay, so once again we see that we support the same kind of operations. All of these have a C at the end of them to indicate that they use a constant as one of the sources. And everything else about them is the same. Of course, just remember that each one of them is going to have a different opcode from the ones without the constant in order for the beta to be able to distinguish what it is that you're trying to do. Okay, so let's take a quick look at how we need to change our hardware in order to support these new kinds of operations. And we find that really we don't have to do very much at all, right? All that's changed is where our second operand is coming from. And so we add another multiplexer with this B-select input, and it just tells you if I have regular ALU operations, use RB. If I have the ones with constant operations, use the sign extended constant. And where is it going to determine that from? That information is going to come from the control logic unit, which is going to see which opcode you have, and based on that opcode is going to set B-cell correctly. Okay, so now we move on to our second type of instructions, which are load and store. Okay, this is what's going to allow us to get data back and forth between memory and our data path, so the main registers that we have in our data path. And if you look at the format of load and store operations, it looks just like the ALU with constant. Okay, so once again, what does this mean for our hardware? It means that we can reuse portions of our hardware in order to support this load and store operation. The second thing that you want to notice here is that the way that we calculate the address for our load operation is that we take the value of register RA and we add it to the sign extended constant. Well, we just did that with an add C instruction, right? So this is basically the same hardware that it would be needed to support an add C operation is all we need in order to produce the address for our load instruction. So the only difference is that now, instead of that being our result, that's going to be fed to the main memory as our address, and then the main memory is going to give us something back. And similarly, we have a store operation, which once again uses RA plus the sign extended constant as its address. And the difference here is that now register RC is going to be written to that location in memory. Okay, so stores are a little bit special. There are a couple things that are different about stores, so you should keep them in mind. The first is that the store operation is the only case where we'll have RC actually being a source operand rather than a destination operand. Okay, and so we will need to add a little bit of hardware in order to support selecting RC as your source. The other difference is that what you're writing to here is this address which comes from constant plus RA. You're not actually writing to a register. So the store is the only operation that does not write to your register file. And so again, we're going to need to have hardware that controls that keeps random data from being written into our register file. And you'll see that when you're actually building your betas in the lab. All right, so how do we use loads and stores? Well, we said that we basically get our, value from memory. So we have our variable x. We're trying to implement the same operation again, y equals x times 37. So x comes from address 1008 and y goes to 1000 and C. And so this simply translates into a load operation followed by a mul C operation followed by a store operation. Now let's just look a little bit more closely at the load and store. So what we see here is that the address is calculated by adding R31 to this address 0x1008. And so what address is that giving me? Yep. Well, R31 is giving me a 0, but I'm adding them together. And so my address is actually 1008. Okay? And so that means that I'm reading this value of x, and I'm putting that value into R0. Then I do my multiply, and finally I store the value that was produced in R0 into this address, which again is 0, the value 0 plus 100C. Okay? Clear so far? Yeah?
Why did we need to include the value 0 in the storing it? Why do we need R31?
So it's not that you need R31, it's that the format of our instruction requires you to specify a register. And so what I wanted to point out here is that if you didn't actually want one, you can always use R31 to indicate that you actually want to add 0 to that value. Okay, and so you'll find that you'll use that. And in fact, we're going to introduce you later on to what we call macros, which are kind of shorthand notations of doing things like this. So instead of having to explicitly specify that R31, you'd be able to ignore that. But for the time being, just so that we're very clear on what the actual instructions that the beta is translating look like, you need to provide a register. Yes?
So what's the format of the store again? What would happen if you put a different register instead of R31?
Then you would add the contents of that register to this address, to this constant value over here, and that would become the address that you're storing a value to. Okay? Any other questions? All right, good. Okay, so we started off this lecture talking about this factorial function, right? And so far our beta does a lot of things, but can it implement this factorial function yet? I see a no. Can I get an explanation for why? What's missing? Well, if you recall from our FSM for factorial, we were doing a loop. right? So far, we haven't given ourselves the capability of doing this loop, right? All we're doing is we're always adding 4 to our PC, which just fetches the next instruction, okay? So we need one other type of instruction, which is called a branch instruction. And what this instruction is going to do is it's going to say, okay, I've gotten to my loop. I actually am in a situation where I have a conditional branch. Depending on this value of b, so if b is not equal to 0, I want to take this branch and I want to go back to the multiply operation. Okay, that would be my branch target. If b is equal to 0, then, oops, sorry about that. Then the branch is not taken, and I just go on to the next instruction, which in this case happens to be done. Okay, so what does that look like? So once again, the format of our instruction is very similar in that we have an opcode for either a B. Q stands for is it equal to 0, branch if it's equal. BNE stands for branch on not equal to 0. And then we have our registers RC, RA, and the 16-bit signed constant. Now, this constant is a little bit confusing, and we're going to spend much more time in recitations going over what it is that goes into that location in your instruction. But just so we're complete here, what's really happening is you're going to store an offset. That offset is going to be measured in words, so in other words in 4 bytes, and it's going to be measured from the next instruction. And so if you try to understand what it is that a BQ is actually doing, it's first going to take your PC plus 4 value, and it's going to store it into register RC. Now, we'll see in a couple slides why that's useful, but basically the reason that it's useful to store that address is once we get into procedures, we want to remember where we came from so that we can go back to it. Okay, and so that's the reason that we store that value of PC plus 4 in this RC register. Then we check our condition, which is the value of RA equal to 0? And if it is, then we're going to do the branch. The way that we do the branch is that we're taking PC plus 4 and adding 4 times this offset to it in order to determine our location. So basically the offset is, you can think of it as a destination in words away. So if I'm, branching backwards, it's going to be a negative number. If I'm branching forwards, it's going to be a positive number that's associated with how many instructions I am away, with the slight caveat that it begins from the instruction following the current instruction. And again, we'll get to plenty of examples in recitation about that. Okay, and then we have our BNE, which is branch on not equal, which is basically the same, except that in this case, you're checking if RA is not equal to 0. And if that's the case, then you update your PC, and if not, then your PC just gets PC plus 4. Sorry, I forgot to mention that over here too, which means that you're just going to the next instruction. And just to avoid some confusion, this NPC is really just a notation to help simplify writing this. It just means PC plus 4. It's not that there's actually some other intermediate register that this value is going to. Okay? All right, so back to factorial once again. Now can we solve it? You should all yell, yes, we can. Okay? And so our state diagram here has changed a little bit, if you noticed, from the ones that we had at the very beginning of lecture. And the reason is because in the very beginning of lecture, we had an architecture that was dedicated to that function, and it actually had the ability to do both a multiply and a subtract in the same operation. In our beta, we can't do that, right? So we've split these things up. And so first we would do our multiply operation. Then we would do our subtract operation. And then we would check whether or not b is equal to 0 and determine whether to return to the multiply or go on to our done state. Okay? So there's only one more instruction. We're almost there. And that is the jump instruction, okay? So what the jump instruction does is it reads the value of a register RA, and it unconditionally sets the PC equal to that value, okay? And so once again, we're going to find that jumps are very useful to us in procedures. And let's take a little bit of a look at how we actually make use of this. So it's really branches together with jumps that are going to allow us to support procedures in our beta. So how does this work? Okay, well, I have two instances of a branch instruction which are going to call this square root procedure, okay? The first instance is located at address 0x100, and the second one is at 0x678. So I come through here the first time, let's say, R31 is always equal to 0, which means I'm always going to take that branch. And so I branch over to here. And what's the second, sort of side effect of branch instructions? Is that I store the value PC plus 4 into my RC register, okay? So our RC register is actually a special register here, R28, which we're going to use exactly for this purpose and this purpose only, okay? So what goes into R28 is the address of the next instruction, which is 0x104. Now I get over here and I begin to execute the square root instruction, the square root procedure. I execute all of those instructions, and at the very end of it, I add an instruction that says jump R28, R31. So the R31 is just telling me that in this case, I don't care about the return address, so I don't need to bother saving that PC plus 4 value. But what this jump R28 is going to do is it's going to bring me back to address 104. So now I'm back over here in my code after having executed the square root function, okay? I then continue and I get to another BEQ to square root. This time, when I go to square root, I'm setting R28 to a new value, okay? I set it to the value of PC plus 4 from this location. So this time, it's 67C. And once again, I'm going to execute my square root procedure, and at the very end of it, I'm going to get to this jump R28 instruction. But this time, R28 has 67C in it, and so now I'm going to jump back to this location in my program, okay? And so even though when we first explained what the way that the branch worked, it seemed kind of odd that we were saving this value in RC, you see now that for procedures, it's really very useful to be able to do that. The one other thing that I forgot to mention in an earlier slide, let's just go back to it just a second, is in the branch, sorry, I can't find it, we'll skip it. But what I wanted to mention is that in the branch, what you're going to do is you're typically going to say, here it is you're not going to actually put the offset that is required in your code itself. Instead, you're just going to use this symbolic label in your programs, okay? And so what does our factorial function look like? Is we have this label L, which just indicates where my loop begins. And so I have my multiply operation followed by my subtract operation. And then my branch on not equal is checking whether R1, which stores the value of this variable B, is equal to 0 or not. And then if so, it branches back to L in order to repeat the multiply. Okay? And so once again, this program, which we call the assembler, is going to do that difficult calculation of the offset for you. So we still want you to understand what exactly it is going to be computing, and that's what you'll go over in section. But as far as writing programs, you're not actually going to be thinking of, what's the offset that I'm jumping to, because if I was to add an instruction to my loop, then all of a sudden, that offset would change. And so I don't want to have to keep track of that in my program. We let the assembler take care of that for us. Okay? That's it for today. I'll see you next time. Thank you.